Hello students, welcome to BTech first year bridge course. In the last lecture, we have discussed about importance of Poisson's equation and Laplace's equation under electrostatic boundary conditions. So today we will discuss the electrostatic boundary conditions in more details. Now when we talk about boundary conditions of electric field, those actually describe how electric field changes across the boundary surface, separating two regions. Now here, this is a charge sheet and this is separating two regions. One is the above of this charge sheet and other is the below of this charge sheet. Now suppose you move from below to above of this charge sheet. Then the electric field undergoes a discontinuity at this surface. Now let's understand this discontinuity in electric field and what will be the value of this discontinuity that can be found out using Gauss's law. Now here to find out the flux we have to construct a Gaussian pillbox because this is a charged plane sheet, right? So the total flux through this Gaussian pillbox is the total charge enclosed by this Gaussian surface divided by permittivity of the free space, and the total charge enclosed is sigma multiplied by area of the flat surface of this pillbox. Now here we are considering the thickness of this pillbox is very small. So the sides of this pillbox contributes nothing to the flux. So the difference between perpendicular component of the electric field above and below the charge sheet is sigma divided by free space permittivity. So this is the first boundary condition of electric field. So it tells that the perpendicular component of electric field is discontinuous by an amount sigma divided by free space permittivity at any boundary. Now suppose we have a boundary between two materials, dielectric materials. So in that case, this will be sigma divided by the permittivity of the material. Okay, that you have to remember. Now let's discuss the boundary condition of parallel component of electric field. And to understand that, let's consider a closed rectangular loop which straddles the charge sheet. The length of the loop parallel to the charge sheet is this small l, and the length perpendicular to the sheet is epsilon. Here this epsilon is very small, that is tends to 0. Okay, so now as we know the electrostatic field is conservative in nature, the closed line integral E dot dl over this rectangular loop will be 0. Now as the epsilon tends to 0, only contribution comes from the length parallel to the charge sheet, right? And we get the parallel component or tangential component of electric field is continuous. So this is the second boundary condition of electric field. Now the boundary condition of electric field in a single form combining the first and second conditions is obtained like this. The difference between the electric field above and electric field below the charge sheet is sigma divided by free space permittivity, and the direction is along n cap, which is the direction from below to above of the charge sheet. Okay. Now let's discuss the boundary condition of electric potential. So let's find out the potential difference between 2 points just above and below the charge plane. So the distance between these 2 points is very small because they are just above. Here B point is just above the charge sheet and A point is just below the charge sheet. The distance between the 2 points is very small, that is tends to 0. Now the potential difference between these 2 points can be written like this. Okay, so as the points are very close to the charge sheet, the path length shrinks to 0. So we get potential above the charge sheet and potential below the charge sheet is same, right? And this is the third boundary condition. So that is the electric potential is always continuous across any boundary. Now discuss another condition. Since the electric field is minus of gradient of potential from the boundary condition of electric field, that is this one, the boundary condition here we can write like this, that is gradient of potential above the charge sheet minus gradient of potential below the charge sheet is minus sigma divided by free space permittivity n cap. Now if we use the definition of normal derivative, which is the directional derivative taken in the normal direction, we get this form of boundary condition. Okay, and that is the gradient of potential or normal derivative of the electric potential is discontinuous by an amount of minus sigma divided by free space permittivity across any boundary. Now using these boundary conditions in any real problem, one can solve the Laplace's equation to find out the potential in a region. Okay, so this is the importance of boundary conditions in Laplace equation. So today I am ending here. In the next class we will discuss electrostatic energy for discrete point charges or charge distribution. Okay, thank you.